Welcome back, ladies and gentlemen. This is the next section. We'll be looking at superposition of waves. But before we do that, let's just take a look at what we've done so far. We've looked at waves in terms of mechanical waves with ropes, slinkies, and springs, basically wave properties, what's wavelength, compressions, etc. So we looked at all of that, all the terminology, questions dealing with that. Waves and slinkies and ropes are considered to be one-dimensional waves. If we look at what two-dimensional waves are, those are considered to be waves in water. So we just skip to this section for a second. So we have studied waves in a rope and on a spring. We haven't looked at reflecting yet. That'll be the next section. Waves on the surface of water travel in 2 dimensions, and sound waves and electromagnetic waves travel in 3 dimensions. So how can 2-dimensional waves be represented? So on a string, we just envision it going left or right. But on a water wave, we can see that it's going in multi-directions. So picturing waves in 2 directions. When you throw a small stone into a calm pool of water, you see the circular crests and troughs of the resulting waves spread out in all directions. So the topmost part of the wave is a crest, bottom part trough. So if we take a look here, if we touched it with our finger or a point source, we know that waves ripple out in circles. So the dark sections here, we could imagine those to be crests. So crest to crest, as you see the little C I wrote here, crest to crest to crest, of course that's a wavelength. And those waves move out in a perpendicular direction from the center. So that's what the red lines indicate here. And I drew the little perpendicular symbol here. So the waves spread out in multi-directions. So you can sketch waves by drawing circles to represent the wave crests. If you repeatedly dip your finger into the water with constant frequency, the resulting sketch would be a series of concentric circles, or what we call wavefronts, centered on your finger. A wavefront is a line that represents the crest of a wave in 2 dimensions. So you can see it's not going out from left to right, it's going out in every which way on this piece of paper. The photo shows circular waves in water. The circles drawn on the diagram show wavefronts that represent those water waves. Whatever their shape, 2-dimensional waves always travel in the direction that is perpendicular to their wavefronts. So we know that here's the wavefronts. It's a circle. So if I'm looking at the pointer now, it's kind of in this direction, and then the direction is this way. So we can see it's perpendicular. If I look here, left to right, it would move out this way, straight ahead. So that's one thing to note there. The direction can be represented by a ray, which is a line drawn at a right angle to the wavefront. When all you want to show is the direction in which the wave is traveling, it is convenient to draw rays instead of wavefronts. The red arrows indicate the waves are the rays that show the water wave's direction of motion. One advantage of drawing wavefronts is that when wavefronts are drawn to scale, they show the wave's wavelengths, as we've seen here. The wavelength equals the distance from one circle to the next, because the wave fronts here are really the crests of those. Okay, so if you touch water at one source, that's the shape. If we look over here, we can also create them another way. A ripple tank is a piece of lab equipment that you can analyze water waves in, and you can adjust the depth, etc. And if we look at the picture here, this is what that apparatus would look like. Instead of dipping it at one point, we could use a ruler or a dowel or a piece of wood here to be the oscillator, which touches the water at a constant rate, a constant frequency. And we would see here, if we had a light source above and went through the water, and on this piece of paper or viewing screen, you would see this. So you'd see wave fronts, except they're all straight lines, as opposed to circles, as we saw back here. Okay, so we can make straight waves, which look like that. And of course, crest to crest, that would be the wavelength. Okay, so slinkies and springs and ropes are considered one dimension, left to right. Wavefronts goes out in every direction here on a plane surface. So that is what a 2-dimensional wave looks like. And then, of course, later on we'll talk about reflection. That's in FC2, or PW2, sorry, Properties of Waves, Part 2. All right. We go back to here now, looking at superposition of waves. Suppose a pulse travels along a spring, meets a reflected pulse that's coming back from a boundary, as shown in Figure 15. In this case, 2 waves exist in the same place at the same time. Each wave affects the medium independently. The principle of superposition states that the displacement of a medium caused by two or more waves is the algebraic sum of the displacements caused by individual waves. So what this indicates is if we have a wave going from left to right, a wave going from right to left, and if they meet in the middle, this snapshot photo indicates them meeting. So we could have started drawing it back here, started the other one over here. What happens when they completely overlap each other is just the algebraic sum. We assume one side of the rope or spring is positive, the other side is negative. So it's like saying I have positive 3, negative 1, so the result, of course, would be plus 2. So that's what the principle of superposition says. When waves interfere, the resulting displacement is equal to the sum of the individual ones. If waves move in the same medium, they can cancel or form a new wave of lesser or greater amplitude. The result of the superposition of two or more waves is called interference. And if we look at the next page, it's a little more clear cut here as to what's going on, because it shows a time-lapse photo almost. So if we look over here, we have one wave here going from left to right, another wave going from right to left. This one's, we can kind of view this as the positive region, this is the negative region. So a split second later, boom, they're closer. And if we assume, like, let's say this was positive 2 and this was negative 2, of course the sum of 2 and negative 2 is 0. So we can see it cancels out there. And then the wave keeps on moving, or the pulse keeps moving as if nothing had happened. So you see this one in the positive region goes, cancels, but then keeps on going. Okay? This area of cancellation is called a node on a wave. Okay? So this is called destructive interference. When we have a cancellation, when the wave pulses meet, that's called destructive. You can think of it, we're destructing the waves, making them smaller. Constructive interference, doing something constructive, making the pulse bigger. So here we could say this is positive 2, this is positive 2. When they meet, they make positive 4. So you can see we don't have a cancellation. In fact, we have that point here on the rope moving to a really high spot. Then, of course, the pulses continue moving as if nothing happened. So this pulse, here, 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 here. So it keeps on moving. So that is referred to as an antinode. It makes a larger pulse overall. Okay? So destructive interference causes cancellations or smaller pulses at the point of interference. And constructive makes a bigger pulse. And if we have different amplitudes here, let's say this was plus 2 and this one's minus 1, plus 2 and minus 1 makes plus 1. And then the pulses keep on moving as if nothing happened. Okay, so that is interference. So if we look at here, the description of that, wave interference can either be constructive or destructive. The first panel shows the superposition of waves with equal but opposite displacements, causing destructive interference. When the pulses meet and are in the same location, the displacement is 0. Point N is called a node, which is considered a point of cancellation. The pulses travel horizontally and eventually resume their original form. Constructive interference occurs when wave displacements are in the same direction, so on the same side of the rope or spring. The result is a wave that has an amplitude greater than those of the individual waves. Our large pulse appears at point A when the two waves meet, and it has a larger than normal movement. So that is called an antinode. The two pulses pass through each other without changing their shapes or sizes. Even if the pulses have unequal amplitudes, the resultant pulse at the overlap is still the algebraic sum of the two shown. Okay? This part here deals with reflection, and that again is on the next section, so we're just going to skip that for now. So with today here, we looked at relating our rope and springs waves generated by them. Those are considered one-dimensional waves. Water waves are considered to be two-dimensional waves going off in two different directions. So if you think of it, we're going across this whole plane surface, this whole piece of paper, and they can either be circular or straight. And then lastly, wave interference back here, in which we have, these could be slinkies or springs or ropes, in which we have constructive and destructive interference. All right, see you again.